Okay, let's look at a simple example. And here's a picture for the example. There's a slope attached to the ground, and there's a mass sitting on the slope, which is connected by a rope and a pulley to another mass that is sort of overhanging. Mass is m1 and m2. The acceleration due to gravity is g, as usual. Let's say we're given m1 equals 10 kilograms, m2 equals 20 kilograms. Let's say theta equals 60 degrees, and no friction. So let's say all the surfaces are frictionless. The pulley is massless and frictionless. In other words, the rope slides over the pulley freely, as well as the pulley spins without friction about its axle. The pulley rope, this rope, is given to be massless and inextensible as before, right? Inextensible meaning the length of the rope remains constant. And you're told to assume that the tension in the pulley rope remains constant over its entire length, right? So the tension transmitted by the pulley, or the force transmitted by the pulley, is constant, okay? So that is given. I just want to make an aside that this assumption can actually be shown based on these things, but we will not show this just yet because it actually requires an additional moment balance equation for the pulley, which we have not officially covered. But basically, you can assume for now that the tension in the rope remains constant, okay? If the pulley is massless and inextensible. I'll come back to this assumption later, but for now we will just assume this as being given in the problem, okay? Okay, so that's the problem, and then you're asked to find, determine accelerations of A1, of M1 and M2. Okay. Of course, the acceleration of m1 will be along the slope, and acceleration of m2 will be, well, vertical, up or down. So let's actually define some sign conventions. So let's say m1, this is a1, okay? So upslope. Upslope is positive a1, okay? Similarly, let's say the mass m2 going down, let's say a2 downward is a2 positive, okay? Or positive a2. In other words, if the mass is going downward or not going downward, accelerating downward, the acceleration is positive. If it happened to be accelerating upward, it will be negative. Okay, so these are just sign conventions, okay? It's important to define these sign conventions because your equations will depend on that. If you get the sign conventions sort of not agree with your equations, what you will end up with is essentially a sign error, like a negative sign extra, okay? So just define some sign conventions, like which directions your accelerations are. For now, we are just going to describe the scalar acceleration, but with sign. Okay, so that's sign conventions. Now the next step is to define sort of the free body diagrams. When you're drawing a free body diagram, really all that should be is the object itself. So that's the object, M1. And there's of course M1G downwards. And perpendicular to the surface is the so-called normal reaction, N. You can call it F sub N or N, whatever you want. And then up the slope is the tension due to the rope. Okay, so that's the free body diagram. And then we have for the other mass, mg downwards, m2g downwards. Upwards tension T. Okay, so those are the two free body diagrams really. Now we can write F equals ma in each direction, so to speak, each relevant direction. For each FBD. So let's call this FBD1. This is FBD2. Let's do FBD2 first. Okay. The acceleration is downward positive. Okay. So let's say for FBD2. So here's where the sign convention comes about very sort of critically. The acceleration is downward positive. So let's say m2a2 mass times acceleration equals. So because it's downward positive, you want to count the downward forces as positive and upward forces as negative, right? So because the acceleration has been defined as downward positive, this is super important in terms of how the sign convention makes its presence felt. Okay, so this is downward positive sign convention. Everything is downward positive. M2A2 is downward positive, M2G is downward positive, and because T is upward, you have a negative sign there. Okay, so that's FBD2. Similarly, we can write an equation for FBD1. You can write it in terms of I and J, right? So you can say, if you define J like so and I like so, we can decompose these equations in terms of I and J and decompose the acceleration in terms of I and J. The acceleration is up the slope, right? Or at least that's the positive sign convention. And there is no acceleration perpendicular to the slope. So instead of trying to write the equations of motion along I and J directions, you can rather write it as along upslope and perpendicular to the slope, for which it is convenient to decompose the forces up the slope and perpendicular to the slope. So so up the slope is T, okay? So let me just redraw the full free body diagram, mg or m1g. This is perpendicular to the slope. And really we want to decompose. This is up the slope, this is perpendicular to the slope, this is up the slope. Mg is kind of in between. So ideally we want to decompose mg into two components, upslope and perpendicular to the slope. Okay, so if you have this to be theta, this is basically 90 minus theta, and then this is theta, okay? So if you want to say this is going to be theta, this is going to be mg sine theta, cosine theta, and this is going to be m2g sine theta, okay? So basically this m1, not m2, this m1g has been decomposed into m1g cosine theta and m1g sine theta, so that the revised free body diagram is going to be m1g sine theta, T, normal reaction perpendicular to the slope, and m1g cosine theta into the ground, okay? So this is essentially free body diagram 1, but redrawn so that the forces are along and perpendicular to the slope. Okay, so this will be more convenient. Now we can write F equals ma up the slope and perpendicular to the slope. Okay, so up slope positive. So we are saying upslope is positive because that's your A1 sign convention, M1 A1 equals T, because T is up the slope, that shows up here, minus M1G sine theta. That's it. That's equation number 2, where this is equation number 1, this is equation number 2. We can write another equation perpendicular to the slope. So 0 equals n minus m1g cosine theta. And this is because this is perpendicular to slope. No acceleration, perpendicular to slope. This symbol means perpendicular, as you may know, okay? So that's equation number 3. Okay, so now we've written the free body diagram and the F equals ma for all equations that we care about, or all free body diagrams that we care about. Now we want to solve for A1 and A2, okay? How many unknowns do we have so far? We have A1, A2, well, N and T. These are 4 unknowns. And then we have 3 equations so far. Need one more equation. What is one more equation for this problem? Okay, is there another equation that relates these quantities? Well, the equation is basically that A1 up the slope has to be equal to A2 down the slope, because this rope is inextensible, which means that if M1 moves 1 unit this way, M2 moves 1 unit this way, okay? So this is what we mean by kinematics of constrained motion. It's basically A1 equals A2. It's basically a relation between accelerations. Okay, so this is equation number 4. And now we can solve for all of them. So from 3, we have n equals mg cosine theta. We didn't really ask for this, but I guess we have that as answer. And then let's use four in 2, we get m1a2 equals t minus m1g sine theta. This gives us 5. And then 1, if you recall, is already m2a1 equals m2g minus t. Okay. So we can add, this is 1, add these two things. So we have m1 plus m2 a1 equals t minus m1g sine theta plus m2g minus t. These gets cancelled. We have g m2 minus m1 sine theta. This is, so what that gives us, A1 equals M2 minus M1 sine theta, G divided by M1 plus M2. That's also equal to A2, and that's the answer. And you can plug in the numbers. That we've given, okay? Any questions about this?